All right, all right, all right. Conservation of energy. This stuff is great. Not saying it's easy, but you'll just see. All right, we'll just go. It's good stuff. Good stuff coming, people, right? All right, here we go. 5 kilogram mass compresses a spring constant given by a distance of such and such. The spring is released and launches the mass onto a frictionless floor. On the floor, there is a 5-meter long mat with a coefficient of friction of 0.1. What is the final velocity of the mass after it passes the friction mat? All right, now I'm just going to say there's going to be a difference between watching these videos and working through the problems with the videos, right? Do not, how to put this, watch these videos in the spirit of trying to learn and work through, because the worst thing that could happen is you have a false sense of knowledge that you think these problems can be done, right? So if you work through the videos, get the solution, when you get to studying, try to go back and do them. Then you'll know. Then you'll know whether or not you know it, okay? Or at least remember it. It's important, right? Because there's going to be quite a few questions on the exam that have to deal with identifying energies and solving conservation of energy problems. All right. With that, let's go. Looks like it's just a straight up guy like here. There's going to be some sort of mat, right? That's a friction mat right here. Some length or distance. Yeah. Okay, call this a length L, sure. And then we have my object. Say it's box, right? The box is moving at a velocity this way. Okay. This is like my initial velocity. This is like, there's the mass. It's terrible contrast, right? Maybe I'll use this. Is that better? That a little bit better. Okay. Let's see. What's the final velocity of the mass after it passes the friction mat? Okay, so I'm going to make another little mass right here. Take it, move it over here. So as long as, like, what's going on here? You're sliding. And what do you expect to happen when you hit the friction mat? You can go, and afterwards you're going to coast along. Just as you were before? No. Where before as in you'll be at a constant velocity, constant kinetic linear energy, but you're going to be slower, right? Some of that initial energy that we have right here in this situation gets, I don't want to say taken away. It's not taken away by the mat, right? Due to these guys, having that friction acting on it, it dissipates some of that kinetic energy into heat in the atmosphere. So afterwards, it'll still be moving because it says what's the final velocity in this case. So it's still going to be moving, but it won't be moving as fast, right? And I can draw my box here right after, all the way over, right? Because afterwards, there's no more friction. It'll just continue on its own little merry way until, it hits a hill or a cliff or another friction mat or a spring, right? But for right now, this is what we have. And I think that's it. Okay, now for the super duper equation, where I'm going to be writing this a lot, right? But the super duper equation is long, but it always reduces. It always super duper reduces to a few of these guys. I don't think I'll start at the beginning. I'm just going to say we're going to start right here, right? The first line is always the same, right? Which is energy initial is equal to energy final, right? I could look at the energy before it hits the mat. I could look at the energy as it's halfway on the mat, but the energy I want to look at is before and after the mat. That's my initial and final situation, right? That's one of the hardest things to figure out. What's my initial? What's your final? Now from here, say, okay, KL initial, KR initial, plus UG initial, plus US initial. Those are all the types of energies I could have initially, right? And I'm going to say this is my initial situation. For each of these, I have a little question that I can ask myself. And the question, whether it's yes or no, is going to answer whether or not the energy is present. Okay? Looking at my mass. Is my mass moving? Yes, it is moving. It has a linear velocity. This sticks around. Next one. Is my mass rotating? The answer is no. It's not rotating. It's not a rolling ball. If it was rolling, that would increase the energy, and that would depend on one half. Until it wouldn't depend on one half. It would depend on its inertia. So things with bigger inertia would have a bigger kinetic energy, and it would depend on how fast it's rolling, omega. Things with the bigger omega means it has a bigger rotational kinetic energy. But in this case, there's no kinetic energy of the rotational variety. So that's X. I'm going to skip gravity for now. Spring. Is there a spring present in this problem? Oh, man. There is. I totally misread this thing. I'm probably like, man, Professor Ray, I didn't know I was moving. I thought I was compressed by a spring. It's because you're right. You are compressed by a spring, right? So I guess I could have left that, though. I'm going to leave that. I'm going to say that I have my brown guy right here. Oh, brown box. Right? This is compressing the spring. Right? Here's my mass. Right? So this isn't my initial situation. My initial situation is right here. Okay, right, I can tell these are going to be long problems, but hopefully good learning happening here, right? I just learned my lesson right there, right? So this thing is initially stretched or compressed. It's compressed some sort of distance, x, right? That is let go. After it's let go, this thing is certainly moving, right? So all of that compressed spring potential energy, which was initially present, goes boing, right? And it's initially at rest. It releases it. It started to move on the frictionless table. So all that potential energy to a spring went into kinetic energy. And then you go over a friction map. Some of that kinetic energy was dissipated by friction, work done by friction. And then afterwards, you are moving at a smaller kinetic energy, and then we account for that lost energy by looking at that work done by the friction, that heat that's dissipated into the environment to raise the temperature of the environment. All right, so now that we have a full picture, right, let's go back and let's ask ourselves, what's the initial situation? The initial situation is I have a mass that's compressed, compresses a spring, and it's at rest, right? So this right here is the initial situation. Mass compressed, velocity equals 0. I do have all this stuff that happens in between, right? But conservation of energy just says that I just have to pay attention to the beginning. I have to pay attention to the end. As long as I have no external forces exerting work between the initial and the final, the energy will be conserved. So as long as I can account for all the energies initially, I can say that's equal to all the initial energies finally. All right. Whew, let's try this again. Now, with this being my initial situation, is my object moving with a linear velocity? The answer to that question for this initial situation is no. It's at rest. It's still not rotating. Potential due to gravity. How do I calculate potential due to gravity? That's mgy. Means I have to define a height, right? Because this height is measured from a reference point. I'm going to make the ground y equals 0. And so if the box is located on the ground, what is the gravitational potential energy? It's 0. So that's 0. Do I have a spring? I do. Is that spring compressed or stretched? Correct. So I start with potential energy due to a spring. All right. Next, final situation. Let's do the same thing. KL final plus KR final plus UG final plus US final plus, I'll say energy due to friction, right? The thermal energy. Final situation is after it's gone across the map. So this is my final situation. After the final situation, right? Do I have a mass and is it moving? I guess I do have a mass. Is my mass moving? Yes. Boy, kind of struggling with this one. Hopefully you guys are following. Okay. Is that mass rotating? No, it is not. Do I have a height that is measured from 0, right? Nope, I don't, because I am at y equals 0. I am not at a non-zero height. Is there a spring? Correct, there still is a spring. It's all the way at the beginning, right? But the second question is really important here. Is that spring stretched or compressed? And the answer is no, it's not. After it's released, it just goes back to equilibrium, right? No, maybe not there yet, right? Maybe some people have used a spring-loaded Nerf gun or a spring-loaded BB gun, right? What do? You cock it somehow, right? And then you fire the BB and the BB's shot, right? But you can't hit the trigger again, right? If you hit the trigger again, nothing's going to happen. Why doesn't anything happen? Well, that's because the spring doesn't have any more potential energy to it. It's not stretched. It's not compressed until you hit the lever action again, or you do the pump action or the pull action or whatever it is, right? You have to give that spring, you have to stretch it again, right? You have to do work on the system to increase the potential energy of the system, right? So there is a spring, but it's not stretched and it's not compressed, which means there's no potential energy due to that in that spring anymore, right? All that potential energy went into, right? This is US, right? All that potential energy went into kinetic energy linear. All that energy then, some of that energy, right, was dissipated by that friction, right? Energy due to friction. And then at the final situation, right? Technically right here, we just have linear, but that friction, I did have friction in between my initial situation and the final situation. As long as there was friction anywhere in between those two locations, you have to include it. You have to include it. So I have to include that friction in the final situation. Right. So the question I usually ask myself again is, from the initial, as my block went from the initial to the final location that I'm analyzing, was there any friction? The answer is yes. Yes, there was. So I have to include it. So a super duper equation reduces to this. See, don't give that, so it gives me a mu times my normal force. Okay, the normal force in this case, hopefully we're all here where if gravity is the only one acting down and normal force is the only one acting up, then that normal force becomes, so USI equals KL final plus mu mg, and L is that length, the length of that mat. Okay. Now, what are we trying to solve for this? What's the velocity after the mass? Okay, so that's buried right here. I don't know why I extended that one. I didn't extend these ones. Sometimes I do, sometimes I don't. So I'm not given the potential energy of the spring in joules. I have to calculate it. So I end up with 1/2 kx squared. I know all those values. It's equal to 1/2 mv final squared. So I'm trying to solve for, plus mu mg times L. Yeah. Okay. Let's see. I'm going to say 1/2. I'm going to make that a 2. And I'm going to subtract 2 mu mgl. So I get kx, right? So this is essentially, well, maybe I won't do the 2, right? I won't do the 2. right? I'm going to leave it here so I can prove a little bit of a point here. I have 1/2 kx squared. I'm going to subtract the mu mgl minus mu mgl is equal to 1/2 mv final squared, right? So I'm saying I'm taking the initial total energy of the spring, I'm subtracting that little bit of energy that was dissipated by that friction mat, and I'm saying whatever is left over is the kinetic energy, right? Kinetic energy of the box. Okay, so from here, that's why I want like, U sub S, friction, K sub L. Right. So now I'll do that too, guys. So we get kx squared minus 2 mu mgl. I'm going to divide that by the mass. Right? If you can't follow this algebra, you're just going to have to do it, right? Can't make these guys super, super long. It's already probably at 10 minutes here. All right, so kx squared. So k is 1140 times x squared. Don't forget to square that, 0.7 squared. And I'm going to subtract 2 times mu, 0.1 times mass, which is 5, times g, which is 9.81, times L, which is 5. Gonna get that, divide it by the mass, which is 5. I'm gonna take the square root of that, about 10. 10 meters per second. 10/s meters per second. And what do we get? We get the right answer. Isn't that cool? Cool, cool, cool. All right. Now, there's no way we'd be able to do this with Newton's second law in kinematics. It would just be over the top. I'm sure there's a way I could figure out how to do it. But when we have conservation of energy that works so well, why would we do that, right? Super duper equation, number 1. Hopefully it was helpful. Hopefully it was likable. Hopefully you learned something, right? Remember, work with the videos. Don't just take it in osmosis and convince yourself you know it when in reality you might not, right? Always a good option. But it's like, hey, you watch the video, maybe just don't put in the answer, but pause, try to do it all again on your own, like either right now or maybe tomorrow, and see if you're able to do it that way, right? Good ways of practicing so that you can practice well, so that you can perform well, right? Practice doesn't make perfect. Practice makes permanent. If you practice incorrectly or in not a great way, you ain't gonna have good results, right? All right. Awesome. Enough of the pet talk from Dr. Ray. Thanks for watching, everybody.